Hello students, have you ever wondered how two hydrogen atoms can bond together to form hydrogen gas, or how oxygen molecules behave in the air? Well, that's where molecular orbital theory comes into play, explaining why atoms combine the way they do and what makes a molecule stable or unstable. Imagine, if you will, that each atom's electrons are like tiny little magnets. When these magnets combine, they form new patterns of attraction and repulsion which hold the molecule together. Molecular orbital theory, developed by Hund and Mulliken in 1932, gives us a new way of looking at atomic interactions, no longer as isolated atoms, but as a network of shared electron clouds. These electrons are not stuck to one atom, instead, they move in molecular orbitals that extend over the whole molecule, making bonding much more complex and fascinating than we once thought. This theory helps explain everything from the formation of simple H molecules to the complex bonding in oxygen and nitrogen. Now, let's dive into how these molecular orbitals are formed. Think about the way you could combine two waves in the ocean. When two waves crash together and their peaks align, they form a bigger wave. This is constructive interference, and in chemistry, it leads to what we call a bonding molecular orbital. On the other hand, if two waves collide but their peaks and troughs cancel each other out, that's destructive interference, which creates what we call an antibonding molecular orbital. In the case of H2, the once atomic orbitals of two hydrogen atoms overlap. This overlap forms two molecular orbitals, one bonding orbital denoted as sigma-1s and one antibonding orbital denoted as sigma*1s. The bonding orbital pulls the two nuclei together, stabilizing the molecule, while the antibonding orbital, if occupied, would push them apart. For molecular orbitals to form properly, a few conditions need to be met. First, the atomic orbitals must have nearly identical energies. For example, two 1s orbitals from two hydrogen atoms can combine, but a 1s orbital will not combine with a 2s orbital because their energies are too different. Second, the orbitals must have compatible symmetries. Imagine trying to fit two puzzle pieces, they have to align in just the right way. This means that a 2pz orbital on one atom can combine with a 2pz orbital on another, but not with a 2px or 2py orbital since their symmetries differ. Lastly, the more the orbitals overlap, the stronger the bonding. The greater the overlap, the more electron density is shared between the nuclei, which leads to a stronger bond. So, for effective bonding, the energy, symmetry, and overlap all have to align. Molecular orbitals come in different types, and each plays a unique role in molecular bonding. The simplest ones are the sigma orbitals, which form when atomic orbitals overlap head-on. These orbitals are symmetrical around the bond axis and are responsible for the strongest type of bonding. Then we have pi orbitals, which form from the sideways overlap of atomic orbitals. These are not symmetrical around the bond axis, and they're often seen in double and triple bonds, like in the case of oxygen or nitrogen. For even more complexity, we have delta orbitals, which arise from more intricate overlaps, often involving d orbitals in transition metal bonding. Each of these orbitals influences how atoms interact, how much energy is required to break the bond, and whether the molecule will be stable or not. Let's now talk about how these orbitals are arranged in energy. In a molecule, the molecular orbitals are organized in a specific order based on their energy levels. For example, when two 1s orbitals combine, they form two orbitals, one bonding, called sigma-1s, and one antibonding, called sigma*1s. This same pattern follows for other orbitals like 2s and 2pz for homonuclear diatomic molecules like oxygen, or we observe an increasing order of energies. Sigma-1s is less than sigma*1s, which is less than sigma-2s, which is less than sigma star to s, which is less than sigma to pz, which is less than pi to px equals pi to py, which is less than pi star to px equals pi star to py, which is less than sigma star to pz. This ordering is essential because the electrons will fill the molecular orbitals in order of increasing energy, starting with the lowest energy orbital. The higher the energy of an orbital, the less stable the molecule becomes if electrons occupy it. This is why the electrons tend to fill the bonding orbitals first and leave the antibonding orbitals empty, ensuring stability. Now, let's tie everything together with the concept of bond order. Bond order is a key indicator of a molecule's stability. It's calculated by taking the difference between the number of electrons in bonding orbitals and antibonding orbitals and dividing that by 2. If bond order is positive, the molecule is stable. If it's 0 or negative, the molecule is unstable. For instance, in the H2 molecule, the bond order is 1, meaning it's a stable molecule held together by a single bond. The bond order also affects the bond length. Higher bond order means shorter, stronger bonds. Additionally, molecular orbitals help explain a molecule's magnetic properties. If all electrons are paired in bonding orbitals, the molecule is diamagnetic and repelled by magnetic fields. But if there are unpaired electrons, as in the case of O2, the molecule is paramagnetic and attracted to magnetic fields. To summarize, molecular orbital theory gives us a deeper understanding of how atoms bond together to form molecules. By considering how atomic orbitals combine to form bonding and antibonding molecular orbitals, we can predict the stability, bond order, bond length, and magnetic properties of molecules. It's not just about what's happening on a small scale. These principles apply to everything from the air we breathe to the materials we use in everyday life. Whether it's oxygen in the atmosphere or the bonds in the plastic wrapping around your food, molecular orbital theory helps explain the invisible world of molecular interactions. I hope this session helped you see how chemistry is more than equations. It's the invisible force behind everything from cooking to cleaning, fueling, and even healing. Catch you in the next class with more fascinating reactions and real-world connections.